Okay, yeah. Welcome everyone to strong field laser physics. Today we will go a bit beyond the direct electrons that we have studied so far. Yeah, so in the beginning this will be, well, more or less direct electron in, say, a non-conventional sense, and then we really go beyond it in the second part of today's lecture. Yeah, for a change, I will, in the first lecture, actually present pretty much everything on PowerPoint slides, and then we go back to the usual way in the second part of the lecture. Yeah, so last week we went from 1D to 3D. We introduced the canonical momentum, which is a conserved quantity as long as the electron only interacts with the laser field. Yeah, so this means we're within the strong field approximation where we neglect the potential of the atom or ion after the ionization process has taken place. Yeah, and then as a nice application of the canonical momentum, we looked at the atto-clock experiment, where one uses more or less circularly polarized light, and we came to an interesting conclusion, namely that the electron actually drifts perpendicular to the field direction at which the field was pointing at the time when the electron was released. And we had a little quiz for that. We'll take a look at the results of that, because that we skipped last time. Okay, so here's once again an overview. So this, I talked about what we did last time. Today we will look at these two nice experiments, which, as I said, go a bit beyond the direct electrons, and then we will introduce the idea of recollision and rescattering. A very powerful idea which links strong field physics to collision physics. And in that process also gives rise to attosecond science. Okay, now regarding our little quiz. Yeah, so you remember we had this circularly polarized field, and we assumed that it ionizes an atom and an electron tunnels here at the time when the electron points to the right. And then we found that the electron will drift perpendicular to this field direction. And now it depends on the direction of the field, whether it's right-handed or left-handed circularly polarized, whether the electron will drift up or down. So we actually asked this question twice during the last lecture, and this is the entertaining result of the first round. Yeah? So it was really a wild mixture of all the answer possibilities that were there. And then at the end of the lecture we did it again, and yes, so everybody found that the horizontal component would be 0, and then, well, there was some controversy whether the electron drifts up or down. Yeah, so well, as I said, this depends on the handedness of the circularly polarized light. Okay, from these circularly polarized pulses, we now go back to linearly polarized pulses, but we will, well, have a special field in a different sense. Namely, we will now make the pulse duration very short. That means that the duration of the pulse, yeah, here, for example, characterized by the full width at half maximum of the envelope, is now comparable to the duration of a single cycle. Yeah, this can be twice a single cycle or 3 times, or it could also be once. And in that case, a new quantity becomes important, namely the carrier envelope phase, yeah, that we call phi. And you can find this again here in the mathematical description of a laser pulse, yeah, where E naught is simply the amplitude of the field. Then we have some envelope function. Here I chose a Gaussian function. Could also be a different function, but a Gaussian is quite common. And that would be that dotted line here. And then we have a carrier wave. The carrier wave is not only characterized by a frequency, but also by this phase offset. And the plots here on the left, they show what happens when you change this phase offset. Yeah, for example, when it's 0, that means at t0, where, assume that here in the center of the pulse, this should be time 0, not 5 femtoseconds. But that's not too important, yes? So we just assume this is 0. We could just introduce here a time offset. This would shift the pulse from the left to the right. Yeah? Okay. Now, if we change this phase here from 0, where the peak of the field overlaps with the peak of the envelope, to, for example, pi over 2, yeah, where now the 0 crossing of the field overlaps with this point, we actually change the waveform of our laser pulse. And so we can go from a field dominantly pointing up to having equal field strength in both directions to a field dominantly pointing down. And since we understood now that the electrons in strong field ionization actually follow the field of the follow the field of the laser pulse and not just its envelope, we could expect that this parameter phi has an influence on the photoelectron spectra. If the pulse were, however, quite long, then of course this asymmetry, namely the field strength pointing up here versus the 2 pointing down, this would be negligible, yeah, if it consists of many, many cycles. Okay, so let's take a closer look at this asymmetry. We have here, for example, a cosine-like pulse. And the cosine-like pulse has this single strong spike. Now, if we calculate the ionization rate for this particular waveform for this pulse, we find that most of the ionization will actually take place around this central peak there. And of course, the shorter this pulse, the stronger this confinement here to the single peak. If, however, we go to phi equals pi over 2 or 90 degrees, and this is what we would call a sine-like pulse, yeah, because it has the 0 point at t equals 0, then we would have 2 equally strong spikes. And now, a straightforward approach to measure the CEP could be the following. Yeah? So assume we have this this laser pulse here. Yeah, so we have, that's not a good color. Yeah, we have our laser pulse here. And now we place one detector here to detect all the photoelectrons emitted in this direction, and one detector here to detect the electrons emitted in that direction. Yeah? And from this intuitive picture, we could think that this allows us to measure this field asymmetry directly. Yeah, so for comparison, I will draw a sine-like pulse. Yeah, this would now have 2 equally strong spikes, and the rest would be weaker. Yeah, so this would, in this picture here, send as many electrons to both directions. Yeah, so by measuring the different yields, we could infer the waveform. Is there? Do you think this is an idea that will work? Yeah. So if you think of the previous lecture and the vector potential, yeah, so this is not quite correct because we need to take the vector potential into account. Namely, here in the blue dotted line indicates the vector potential. And now the vector potential is actually has no asymmetry for the cosine-like pulse, and it has an asymmetry for the sine-like pulse. I can draw an enlargement here. Yeah, so in this case here, the strongest direction down would actually occur for the sine-like pulse. Yeah, but nevertheless, in this case, actually an asymmetry remains for the sine-like pulse and not for the cosine-like pulse. Because here, so most of the ionization takes place here, and there we have a symmetric vector potential. Yeah, so therefore the photoelectrons emitted to the left, or the spectra emitted to the left, and the ones emitted to the right are equal. Different in this case. So in principle, one could do this, and we can now go ahead and actually calculate the photoelectron spectra using, for example, the Simpleman's model for these two pulse shapes. And this is the result. Yeah, so we start here with a cosine-like pulse. There, so there the momentum distribution here along the polarization. Yeah, so this is only the momentum component along the polarization. The spectrum here is the same as the spectrum there. If we, however, go to the sine-like pulse at pi equals 1, Cp equals pi over 2, that would be this one here, we actually have more electrons going up than going down. Yeah, so there's an asymmetry. And then this oscillates back to the symmetric case in case of the, minus cosine-like pulse. And then we have an asymmetric momentum distribution, but tilted in the opposite direction as before for 3 pi over 2. Okay? And a convenient way to display this asymmetry is to calculate what we call the asymmetry parameter, where one simply sums up over the, say, negative part of the spectrum, which we call arbitrarily left, and this one we call right. And then we calculate an asymmetry as right minus left divided by right plus left. And we can do this for each momentum and for each phase. So if the value here is negative, this indicates there's a dominant electron emission to the, in this case, left side. That would be negative. Yeah, left is larger than right. And opposite in case of the positive signal. Yeah, now if you think back of this phase meter idea, where you have two detectors, you can directly measure these values R and L by simply counting the electrons with it arriving at the detector with a certain energy or momentum, and then measure this asymmetry. And in principle, if once you have calibrated it, you could find the phase depending on the value that you detect here. Yeah, depending on the value of the asymmetry. And this is, however, still not the full picture. Yeah? If you take into account the Coulomb potential, the attraction by the core, then you will actually see a phase shift here. And then the cosine pulse will not produce zero asymmetry, but some asymmetry will remain, and likewise for the sine pulse. But this is mostly a phase shift. So, yes, please.
Regarding the asymmetry, the highest asymmetry is around, or highest intensity is around 1.1.
Mm-hmm.
And how does that correspond to the previous figure that one? Can't relate the two figures to each other.
So the question is, how do the two figures relate to each other? Yeah. So for each, we call the upper part we call L, yeah, and the lower part we call R. And then we actually have, so basically we now have two separate figures, this one and that one. Yeah, and then we calculate the asymmetry according to this, which means essentially, for example, say at this particular phase here, we would compare the value at minus 0.5 to plus 0.5. Yeah, and then you get this asymmetry here. And the maximum here is also the maximum there. Only because here we normalize the difference to the sum, we can actually see signal where on a linear scale you don't actually see anything on the left-hand side. Yeah? And it will turn out that once we include rescattered electrons, we actually have a way to measure the CP that works much better than this. And we will get back to this, and then you will get, so actually in the next homework session, you will get a chance, you will get a chance to calculate these CP-dependent asymmetries. And well, maybe one more remark regarding this. There's that this idea actually works better with a circular polarization for direct electrons, because in that case, once you have a very short laser pulse, maybe let's go back to this one, which is circularly polarized. Yeah, circular polarization consists of an oscillation, well, you could write it like, so this is now the envelope function, and now you have cosine, I need more space, so write it in the next column. Yeah, so you have cosine omega t plus phi plus sine omega t plus phi. But this could also be, sine, of course, is nothing else but cosine omega t plus phi plus pi over 2. Yeah? And now this means you will now actually have a two-dimensional asymmetry. And what will happen is that you no longer have a donut-shaped electron distribution, but more of a crescent, like a half moon. And this half moon will then rotate as a function of the CP. And this works in principle much nicer to determine the CP, because then with these two-dimensional measurement, you actually have, you can really relate an angle of electron emission to the CP. Whereas in the case of linear polarization, you only have the single number. And there, of course, you run into the problem that, for example, this phase gives you the same asymmetry as that phase. And same everywhere else. There's always two values that give you the same CP. Or the two CP values that give you the same result. Okay, so that's for the phase meter. The next experiment is a bit more involved. Are there questions regarding the phase meter? Okay, so we'll get back to the idea after we introduced recollision. Okay, so the next experiment is. Yes, please.
How much or how far it has a resolution for the CP?
Yeah, how well can the CP be measured with a phase meter? So using recollision, so the actual phase meter that we use down in the lab achieves roughly 100 milliradians. Yeah, so you have 2 pi radians for the full range, and the precision is roughly 100. If it's well aligned and you have a good signal. More typically, it might be 200 milliradians, which is actually comparable nowadays to what can be achieved by a direct stabilization of the phase. Okay, so the attosecond streak camera. So this goes back to high harmonic generation. High harmonic generation. You remember, of course, from well, from the first chapter on the fundamentals. One could say that high harmonics are produced as a byproduct of strong field ionization. So one simply focuses a laser pulse, an intense laser pulse, into gas, and then one can observe harmonics. However, to make an intense source, the whole story is a bit more complex. We will actually discuss this in detail in chapter 8, which focuses on phase matching issues in high harmonic generation. But nevertheless, one can use these high harmonics for a very interesting experiment, which nicely fits into our story of direct electrons. And understanding that experiment gives also a nice perspective on getting a deeper insight into these whole direct electron dynamics. Yeah. So if you really have your high harmonic generation well controlled, you can even use it to generate a single attosecond pulse. This is shown down here. Yeah, this is a single pulse in the XUV spectral range that has a duration of round about 200 attoseconds, and it's therefore much shorter than a laser pulse. So if I were to draw schematically what happens here, you sort of see this here, but this is using kind of a complex laser field that's not actually necessary to generate an attosecond pulse. But one can typically use a few cycle laser pulse as we introduced in the previous section. Yeah, so what one would do is you have a laser field, a laser pulse, and then you place the attosecond pulse somewhere in the middle. Yeah, so for example here. Yeah, and this is, as mentioned, this whole duration here is shorter than a half cycle or so of this attosecond pulse. And then one can scan the position of this attosecond pulse with respect to this laser field. Okay, how this is done is actually displayed nicely here. Yeah, so this is one way to do it, more sort of a straightforward, simplistic way. One could also build an interferometer where one would then recombine both beams. But this is, well, essentially a collinear interferometer. So the light is here focused into this gas target where the XUV, the attosecond pulse, is generated. And then one propagates through this zirconium filter on a pellicle. Yeah, so this, the pellicle is a thin foil, 10 micrometers or so, and that does not transmit any XUV light. However, it can transmit the visible or infrared light used for the generation. And in the middle of this, this foil is cut out and replaced by a metal foil. The metal foil, in this case zirconium, has a thickness of only 100 or 200 nanometers or so. And this will actually, because it's metal, not transmit the infrared light, but it will transmit at least 50% or so of the XUV light. Yeah, and then back here, you have a mirror with a hole. And in this hole, you stick a smaller mirror that you can delay with respect to the outer mirror. Yeah, and by that, you can introduce a delay between the infrared and the XUV pulse and really scan this back and forth. Okay, so what will happen now when we ionize or when we focus these two pulses onto another gas target? Yeah, so we have now an XUV pulse. Yeah, XUV, that's photon energies of the order of 50 to 100 electron volts or so. So they can ionize any gas with a single photon. Yeah, so in an energy diagram, this would look like this. We have here our ground state. We have here the continuum. Yeah, so this is the ionization potential. And now for the attosecond pulse, a single photon is enough. And this attosecond pulse carries some energy, h bar omega, and then this photoelectron energy here, this will be h bar omega minus the ionization potential. Yeah, so this is straightforward. But all of this, of course, happens in the presence of this infrared field. And the way the experiment is designed, this infrared field is actually very intense when it generates the harmonics. But then, after the refocusing, it's actually rather weak. So it cannot ionize the system itself. However, it can nevertheless deflect the photoelectron that's then produced by the XUV. Yeah? And this situation is actually similar to the case, to the standard way of strong field ionization. Namely, there in strong field ionization, we have an electron that enters the continuum and is then accelerated in the laser field. Here, the electron enters the continuum at the time of the XUV pulse, namely this time here. So this will define time 0.
And then it will be accelerated with the fundamental field, right?
Yeah, it will experience the acceleration from the laser field. And this is shown in more detail here. Yeah, so the electron is emitted here by the XUV pulse, and it has an initial velocity, namely, the one, we can convert this here to a velocity. So let's maybe do this. So V0 would be now, well, 2m square root e. Oh, sorry. Yeah, so the kinetic energy is, of course, half over times v squared. Yeah, so v would be 2e over m square root. Yeah, and for e, it's EE, this electron energy, we would plug in this value here. Yeah, so we have an initial velocity that's different from 0. You may remember that in chapter 2, we made the statement that the initial conditions for our simple man's model can be manipulated with attosecond pulses. And this is how. Yeah? By choosing a different photon energy for the attosecond pulse, you can get a different initial velocity. Okay, so one other interesting aspect is that now the conditions of which are assumed by the strong field approximation are here now actually better fulfilled than in the original case for which the strong field approximation was developed. Yeah, because here the electron is already ionized once it feels the laser field. Okay, and good. So we can now. So here once again, this is shown here. The laser pulse, the attosecond pulse produces the photoelectrons, and then they experience, as before, a shift through the vector potential. And we can actually use the canonical momentum to calculate this. Yeah, so we can write down, as we did for strong field, for regular strong field ionization, we take the canonical momentum at time 0. Sorry, this is t0. Maybe it's smarter to write infinity here. And this is the same as the canonical momentum at t0. Yeah, and then this is, of course, mv at time infinity plus the vector potential at, or E times the vector potential at times infinity, which is, of course, 0. And this must be the same as for, so what's going on here? Okay, that's strange. Okay, I cannot write there for some reason, so I have to write somewhere else. Okay, the here it's okay. mv at infinity. Nope, it's not okay. Anyway, so you plug in m times v plus e times a. You do this for time infinity and for time t0, and the resulting drift velocity is then v of t naught, yeah, which is the initial velocity that the electron gains from the XUV pulse, plus e divided by m times the vector potential at time t naught. Yeah? Or, as shown down here, you can think of it that the laser field induces a momentum shift equal to the vector potential. So what's really different here as compared to regular strong field ionization? Yeah? Yeah, at time t naught, we can have a non-zero vector potential. Well, I mean, we could have that before, but we couldn't control it, right? Yeah, so most of it actually came when the vector potential was non-zero. But here we can fully control it. So we can actually, if we scan this t naught across the entire pulse, then we can actually map out the vector potential. We can directly measure the vector potential, and that is what's done here. Yeah, so this shows actually the photoelectron energy. Yeah, so for this, we need to calculate the. It's not important. We need to. Thank you. We need to calculate the energy from the velocity, and the result is. Yeah, so we simply square. Basically, we just square this result here. Yeah, and then the result is that the drift energy is 1/2 mv of t naught. Yeah, that's the initial energy, plus 1/2 e squared over m times vector potential squared. Yeah, so this is essentially the acceleration that comes from the laser field, depending on where it goes, where it's initiated, where it's ionized, yeah, because the vector potential goes up and down. And now we also have a cross term, yes, because when we square this, we also get this cross term, and this cross term is the most interesting one. Namely, it looks like this: E v of t naught times a of t naught. Yeah, and now if you change. Now, what happens if you change t naught? This one doesn't change, yeah, because it's only given by the energy of the XUV. This one, of course, changes somewhat, but because the intensity of the infrared in our case is now not very strong, this just changes a little bit, and it modulates the width of the momentum distribution, of the energy distribution. And this one here actually represents an oscillation. Yeah, because this one doesn't change, but this one goes up and down. And this is what you see here: up, down, up, down, up, down. And now, if you look at this closely, you see that the distribution is wider here and there as here and there. Yeah, and that's the width. That's this term here. Yeah, so this. Oh, this is the wrong. Yeah, so this is the width. This is the offset, and this one is the oscillation. Is there a square in the offset? Yes, of course. V squared. Yes, thank you. Yeah. the oscillating part. Yeah, so the origin of this is that when you square this, you get of course this one squared, you get this term, the second term squared, but you also get the cross term. Yeah, it's a plus b squared, you get a squared plus b squared plus 2ab squared, and that is this term here.
Yeah, I know.
Yeah, and then that's this here. That's this oscillation. Yeah, it's this oscillation here. So this is essentially a direct image of the vector potential of the infrared field. And if you, because this is the vector potential, you can just take the derivative, and then you know the electric field as a function of time. Yeah, and this is what they did here in this experiment, and they retrieved here the waveform of the laser pulse that they used. And and because they argue that this is the first time that a light wave was directly measured, they published this paper here. And well, they actually published a second paper in which they show that you can not only measure the temporal shape of the infrared pulse, but also the one of the attosecond pulse. Yeah, you get that from the same paper, from the same measurement, but they published 2 papers out of this same measurement. The other one was in Nature, I think.
Why do you get the attosecond shape?
Well, there's that's actually explained here. Yeah. So the idea. Yes.
Yeah. So this oscillation part is the vector potential which we take the derivative to get the electric field from, right?
Yes.
And the electromagnetic energy is determined by the time of flight of electrons to reach the
Yeah, this is how we measure the time of flight in order to calculate the energy of the electron. Yes. This is how it's measured. Yeah, this one?
The previous one. The scanning.
And this? Yes?
The attosecond pulse is by the delay.
Yeah, you scan the attosecond pulse with respect to the infrared by the delay. Yeah, and then you for each delay value you record a photoelectron spectrum. Yeah, so at this delay value, this would be just this rather wide distribution around 70.
Okay, at time equals 0 is where the 2 pulses overlap.
Yeah, exactly. At time equals 0, they overlap, and then because the attosecond pulse is so short, you really sample the vector potential at a very specific time. Yeah, which is shown here, and by that you can map out this light field. Okay, and now, so why can we also measure the attosecond pulse? That's when you, okay, this is a bit busy, right? This plot here. So shown here is the laser field, and now this is the vector potential, and now we assume that at this point here, there's an attosecond pulse, and this attosecond pulse is actually chirped. Yeah. So first of all, the duration we can estimate from, or we can actually retrieve by doing a fitting procedure. Yeah, because if it were just a delta function, then this would be narrower than if it's wider. And if you do an iterative algorithm, you can actually find the width, and then you can even find the chirp. Yes, and that's because when this attosecond pulse is chirped, which means, for example, the blue light arrives later than the red light, yeah, it's shown here, then the red part will experience a different acceleration as the blue part. Yeah, because the red part, which arrives earlier, will see a different vector potential as the blue part. Yeah, and this will actually stretch the momentum distribution as shown here in this particular case. And now we put the same attosecond pulse a half cycle later when the electric field is not going from, or the vector potential is not going from high to low, but it's going from low to high. And now this will be reversed, and then the momentum, this energy distribution or momentum distribution of the electrons will actually be squeezed. Yeah, and from this you can reconstruct the chirp of the attosecond pulse. And if you do a spectral measurement and you know the chirp, then you can also find the pulse duration, in addition to this estimate or this rather rough value that you get from the smearing out because of the width of the attosecond pulse. And I found this is nicely shown here in that paper. Yeah, so here this is what the squeezing and spreading out does. Yeah, so if you have no chirp, this looks symmetric. If you have an up chirp, then it looks like there is less signal because it's spread out over more energies. Whereas in this part, it's squeezed together, so it looks like there was more signal. Yeah, so this would be the up chirp, this would be the down chirp that's inverted. Yeah, then they can really measure very accurately here the chirp, the dispersion that the attosecond pulse has. Okay, so this is, yes, please. Yeah. So the color bar here, this is the number of electrons detected in a certain energy bin. Yeah, so these I maybe should have taken more time explaining these 2D plots. Yeah, so as I said briefly here, yeah, each column is a single measurement, is a full photoelectron spectrum. And now we plot one photoelectron spectrum next to the other. And because three-dimensional plots are not very easy to grasp when looking at them, we use colors to represent the height, basically. Yeah, and then this shows here that this photoelectron spectrum has a different value than when you look here or here, and so on. Yeah, and so once again, this is just the number of counts. And when you spread out the energy distribution, it looks like there were fewer counts.
So this, you take one spectrum of this whole.
Yeah, you take one spectrum.
And you see the effect of changing the vector potential in this only single spectrum.
No, on the combination of all of the spectra. Yeah, so these plots here are a combination of, say, 100 or maybe even 1,000 single measurements. And then the first measurement was taken at a specific delay value, which is not shown here. Yeah, it would be shown there, but we can go back here. Yeah? So you do a first measurement at a delay of -8 femtoseconds. Then you do the next one at a delay of maybe -7.8 femtoseconds, then -7.6, -7, and so on and so forth, until you arrive at 13 femtoseconds, and you did maybe 500 spectra. And then you plot one spectrum next to the other to retrieve this. And in this, I don't know what, in the series of spectra, you can then reconstruct the laser pulse from. Okay. So these were some examples of how you can use attosecond streaking to measure the laser pulse or the attosecond pulse. And you can, but this technique can also be used for a pump probe experiment, yeah, which means a time-resolved experiment where you can observe, in this example here, the dynamics of ogdk. Yeah, so okay, there's another question regarding the pulse characterization. Okay, go ahead. Sure.
Yeah, what is the GDD?
GDD is the group delay dispersion.
Yeah, and what these values mean, like, for positive and negative?
Yeah, okay. So positive means that, yes, it's a question of, is it? Well, the difference between positive is whether the blue light comes first or the red light comes first. One can easily get confused which one is which. Yeah, but it basically means that, well, if you have a very short laser pulse, then all the frequencies that are contained in this laser pulse have to arrive at the same time. Yeah, so this group delay dispersion is flat. Yeah, this means they all have the same phase at a specific time. Of course, when you change the time, the different frequencies acquire different amounts of phase. But at time 0, there's a certain phase offset. Yeah, depending on the frequency. Yeah, so if there's a common phase offset, this would be the carrier envelope phase. And if there's a phase offset that depends on the frequency, this is the group delay, or the group delay dispersion. And this determines what color arrives first or second.
Yeah, so for the positive group delay, you have this red part moving faster than the blue part.
Yes.
And it's like, is it like this, at the second pulse also have sided wave packets? So
Yes, yeah, of course. The attosecond pulse is also a wave packet, yes. Yeah, because it consists of many frequencies. I mean, you can see this here, like this. The width of this energy, of the photoelectron energy distribution is 10 eV or so. Yeah, so this must also be the width of this attosecond pulse. So the attosecond pulse really has a really large bandwidth, several electron volts, and this is actually the reason why it's so short. With visible light, you couldn't even create such a pulse because visible light has only 1, 2, or 3 electron volts of energy. So you can't put 10 electron volts in the visible spectrum.
and also using this technique, you can create a transformative pulse in the attosecond dimension.
Not using the technique, but you can use the technique to characterize it. And so this was actually published by a group that develops chirped mirrors for attosecond pulses. And this is exactly what they want to do. Yeah? They want to generate a Fourier limited attosecond pulse. And these are measurements to characterize the pulse. And I assume they had different mirrors there that they tested in this measurement. And this is what they show there. Okay, so I'd like to show you one more example of what attosecond streaking can be used for. And namely, to observe the dynamics of ogdk. So ogdk happens when an inner shell electron is ionized from an atom. Yeah, so first of all, this shows here different energy levels in an atom. Yeah, so you have the valence electrons here. This would be the outermost valence electron, inner valence, and then you have core electrons. And now, if you ionize a valence electron, yeah, then you get a high energy photoelectron. Of course, we're talking about the attosecond pulse here. Now, if you ionize a core electron, then the energy is lower because the binding energy is much deeper or much higher. So once this happens, one of the outer shell electrons can recombine here, and then its excess energy can be emitted as a photon, or it can be the energy can be transferred to another valence electron, which is then emitted, and this is the ogdk. And of course, these processes they likely take some time. And before attosecond science came along, it was not known very well how long these processes actually take. Yeah, so you can maybe measure the line width of the Auger spectra to get some limit to it, but a time-resolved measurement had not been performed, but it can be done with attosecond streaking. And the idea is as follows. You use the attosecond pulse to, well, of course, also ionize valence electrons, but in particular these core electrons. And this is shown here. Yeah? The photoionization, this takes place around the arrival time of the attosecond pulse. And then this triggers the Auger decay. And the Auger decay takes a bit longer. So it takes place later in the pulse. And now if you overlap your attosecond pulse with an infrared laser field, Yeah, so this is our infrared laser field, and we have here, for example, our attosecond pulse. Yeah, the electron emitted by the attosecond pulse experiences some deflection. Yeah, and actually, at the time at which this experiment was conducted, there wasn't really any deflection observed, but rather a broadening. The reason for that is that the phase of this laser pulse was not stable. And then one time it's kicked in this direction, one time it's kicked in that direction, but it was just the phase fluctuating of that laser pulse, not the delay. Yeah, and then, so what matters here actually is not so much the field, but rather the envelope of the field. So the photoelectron will actually observe some strong broadening if you put it in the middle of the field. And then as the ogdk takes longer, the ogdk will experience this somewhat less broadening, yeah, this og electron. And by measuring this broadening relative to the other, one can then track how long the ogdk takes. In particular, this delay time here. Yeah? And this is the experimental result. Yeah, so this time we actually plot a 3D spectrum now. Yeah, so we have here the delay as before, and this is the energy of the electrons. You see here photoionization from the 4p shell of krypton. Yes, and you see here this broadening that takes place there. And then here you see some changes in the Auger electron distribution. So what actually happens here is that there are different lines that then interfere. So it's not such a clean broadening as you see here, but it's rather interference between different lines. But nevertheless, one clearly sees an effect here in the Auger electrons. And yeah, this part, by the way, this part of the spectrum is probably increased in size to make it clearer. In particular to show this part here. And then, well, they make some projection to look at the time delay dependence, and they see roughly an 8 femtosecond delay between the photo emission, yeah, the direct photoionization, and the ogdk. Yeah, so this infrared field here acts like a clock to tell, like, now the electron is coming out. And I mean, this was, of course, at the time a very revolutionary measurement, because this was the first time something was tracked with sub-femtosecond precision. And then over the years, the technique was improved. In particular, what helped was the stabilization of the carrier envelope phase, so you can not only see this broadening, but even shifts. And then, for example, what was measured there was a time delay between photoionization from 2 different shells. Yeah, so this was done in a neon atom, and they can photoionize the 2s shell or the 2p shell, and then observe that there's a 20 attosecond time shift between the two. Yeah? So the deeper lying, the electron, which is more deeply bound, takes a bit longer to be ionized, to arrive in the continuum. And the precision here was 5 attoseconds. And then a few years later, they even crashed the attosecond precision. Yeah? So this is another process, this time in helium, and there they observed a delay of, that actually depends on the photon energy of 10 or 5 attoseconds with a precision that's round about an attosecond. And one aspect that I find very interesting is that the pulse duration of the attosecond pulse is still something like 100 or 200 attoseconds. But the precision that they achieve in these measurements is much less than that.
Because they are taking the difference, but still.
Because they're taking the difference, yes. But the reason is you don't need, you can, if you have a pulse of a certain width, Yes. So this is the width, but you can measure better than that, right? It's the so the error, the measurement error is actually the standard deviation of the mean. It's not the standard deviation of this pulse. Okay, this is what I wanted to tell you about these two experiments. We'll take a 3-minute break or so, and then we'll continue with recollision.